Stars are whispering tales of old, planets spinning, stories bold. Life is dancing through the night, countless worlds in the starlight. Galaxies full of mystery, infinite in their history, beyond our dreams and our sights. Life blooms in the cosmic lights, dancing on the edge of space. Take me away, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Nebulas with colors bright, birth new wonders in the light. Comets trail their sparkling tears, life endures through the years. In the silence of the void, every heartbeat is enjoyed. From the depths and to the heights, life expands through cosmic night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night.
Hello everybody, welcome to SkyTour live stream. It is I, Mark D'Antonio, here with you, and of course, you'll never guess who's here. Yes, you will, you know who it is. It's Daryl. How you doing, Daryl?
Hello, Mark. I'm well. You? Hello, everybody.
I'm doing great, thanks. So guys, this is a wonderful night. It's beautifully clear out in the desert, and I thought it might be a good time to hang out and look at some very cool and somewhat obscure objects out there that we have yet to look at. You may not have seen these before with SkyTour Livestream. I'm actually pretty sure that you haven't seen all of them. And I did a preliminary test of all these the other day just to see how they would look. And actually they look pretty good. So we're going to check them out. First things first, I'm just going to finish up one last thing. And then we'll be ready to go. And here we go. There we go. Okay. I put on the stream lights. Okay. So right now we are in Orion's hunting dog, Canis Major. Okay, this is Canis Major right here, the hunting dog of Orion, and of course Orion is up there. And we're actually looking. What's that?
He's chasing the rabbit.
Oh yeah, he's
Lepus,
chasing Lepus, the hare.
Lepus the hare.
That's right. All right. And then over here is what that looks like in real life. This is Sirius live in our sky, and you can see it there. Sirius is about 8 light years away, a little bit over 8 light years away, and it's really quite a beautiful star in a telescope. Very, very bright, often mistaken for a UFO, in fact, when it's low to the horizon. So it's pretty cool.
It's the brightest star in the sky, as seen from Earth. It's a type A star, if I remember correctly. It's not nearly as bright as an O or a B star, but it is a class A star. It looks white. To my eye, it often has a blue tint to it, and sometimes Sirius is considered the Christmas star. It's a famous twinkler because people see it when it's low and when winter is beginning, and it twinkles a ton and it changes color a lot, which reminds people of Christmas. Sirius is also a double star. There is a white dwarf orbiting the primary star. I have never seen it. You need pretty demanding conditions to be able to pick it out. It's a tiny little white dwarf orbiting the main star.
Yeah.
So it's got that going for it.
Yeah, and being 8 light years away, I often get the question, what if Sirius went supernova? Well, Sirius isn't large enough, more massive enough to go supernova. So, but if it did, it could technically injure us from that distance. It wouldn't, if it was a massive star, it could be somewhat dangerous for us because of the radiation that might reach us at some point. Now, when a star goes supernova, especially the massive stars, they're usually very, very large diameter at that point. All right. And so the core is where the supernova begins. All right. And again, Sirius can't do this, but the core is where the supernova begins. And it starts with the core collapsing because it's now out of its fuel, and gravity wins and starts crushing the core down. During that crushing process, neutrinos, high-energy particles, are released from the star in all directions by the billions. And only 1 in a billion actually gets out of the star because they're colliding and hitting and getting absorbed by other energy-producing areas in the core. But as they spew out of the star, they leave the star and go out in all directions, like I said. And if some of them reach us, we can say, hey, we just got a neutrino burst from this location in the sky. Let's use Betelgeuse as an example. And so a neutrino burst from Betelgeuse, even though Betelgeuse doesn't look any different in the sky than it does now, that means the supernova is underway. And that means all telescopes go to Betelgeuse, and within maybe a couple of an hour or two, those particles that are making their way out of the interior of the star reach the surface of the star. And when they do, the star then explodes. So neutrinos are the precursor to a visual supernova explosion. I'd love to see that.
As for Sirius, there's some interesting tidbits about it. The ancient Greeks, I suppose, and people back then, often described Sirius as ruddy, R-U-D-D-Y, ruddy, which means reddish, yet we see it as a bright white or bluish white star. There has been some debate over whether something with the white dwarf around Sirius has changed since ancient times, and people might have seen something going on, in the white dwarf forming, where they saw a red star and now we see a white star. But conventional process of a star turning into a white dwarf, we don't see a planetary nebula or anything of the sort. It's just one of those odd little bits from ancients to the present. Uh, and also, another little bit, there's a tribe in Africa,
Oh, the Dogon.
thank you, the Dogon, who the tribal awareness, they know, they said that Sirius has another star with it, and yet they don't own any telescopes, and how would they ever know that there was a white dwarf orbiting close to Sirius? It may just be that they heard this and they're repeating it now, but they seem to know more about the star Sirius and its companion than they should.
I was thinking about that, and and even years and years ago, I was studying Sirius to try and figure out what chronology could account for them seeing two stars. And the obvious chronology is that they saw a red star and Sirius partnered with each other, okay, in the sky. So there would have been a beautiful double star, probably potentially a visual double. And there are cases where the white dwarf might spiral in toward the star over time. And so we could be seeing that snapshot in time of where the point where that white dwarf is now close to the star, when it may not have been in the beginning. But the chronology doesn't work. It takes more than a few thousand years for this to occur, as far as we know. Could something have accelerated that process? Could something have caused Sirius to have a partner star that was a red giant that shrunk down without leaving its outer layers behind and make a planetary nebula? And there's a lot of questions. But the Dogon, as you mentioned, is a very interesting mythology. However, it may be based on fact, ancient fact. And so that's still an area that's open research, is trying to figure out what the star is doing, and its partner are doing. So it's a fascinating star.
Can you go back to Stellarium for a moment?
Yeah.
Just show the constellation. All right, you see there's Orion up in the top right corner, just out of view. And then there's the dog, the big dog. And the little dog is above the big dog with Procyon. But the big dog down there, you can see his figure. You can take away the animation if you want. You see the stick figure. I mean, that's a dog. You see its head. Sirius appears, if I had to guess, it's probably the dog's heart. But it's right there at the top of his chest. And his two front legs, I mentioned last stream, the one leg leading out front, the star's name is Merzam, and that means the announcer or the herald, and Merzam comes up just before Sirius, so it announces Sirius is coming.
And let's actually do something to show people what that looks like. Let's remove the constellation lines, and let's remove these objects so you can see just the stars. Okay? Now, you can see these stars, and so from these stars, imagine, as you're one of the ancients, you actually see a pattern in the sky. Do you see this in the sky? No, but you can imagine seeing that together. Orion's pretty obvious, because when you look at Orion, you got these beautiful 4 stars and this belt of 3. I mean, it looks like somebody's standing there. And if you have dark skies, you also have this arc of stars over here. And so when you actually look at Orion, you can see that he's holding something. You could imagine him holding something. You could imagine that Betelgeuse is the armpit or something. You might imagine this as the 4 sides of a human body, the 2 shoulders and the 2 legs and so forth. And that's just what they did. And you imagine a sword hanging down here. So that's easy to visualize. Scorpius, the scorpion, is one of the few constellations that actually looks like what it is, a scorpion in the sky. And Daryl has a great story that he talks about why Orion is on the opposite side of the sky as Scorpius.
Yeah, the scorpion killed Orion, and the gods put him up in the skies, and they put them on opposite sides of the sky so they would never fight again. When you see Sirius there, imagine you're standing the night watch around the campfire many thousands of years ago, like Stone Age days, and you're keeping watch at night, and well, you get used to seeing the same stars every night after a while, and maybe you're bored, so you start playing connect the dots with the stars you see. And through repetition, from night after night of the night watch, and maybe the shaman is staying up late with you, well, these images get reinforced and built into the culture. And that's how that works.
Yeah.
And they didn't have TV back then, and so they put their stories up in the sky for everybody to see and to learn by heart.
And that works very well. I mean,
Homer Simpson saw cowboys. I mean,
right.
The ancients, they saw dogs and hero hunters and unicorns and all that good stuff.
Yep. Yes, sirree. Okay, so and so that's Sirius, the brightest star in the sky, right there. And we're going to take ourselves now to something else I'd like to see, kind of in the neighborhood. And we're going to do a search. And we're going to go to... I want to take us to... Not that. Is it this guy? Yeah. Okay. This is the nebula called Dryer's Nebula, and we're going to look at a really cool location up here. It's actually, let me turn on the boundaries of the constellations. It's in the constellation of Monoceros up here. Monoceros meaning, single horn. That's a unicorn. Ta-da! There's a unicorn. And right over the unicorn's horn is this little nebula. So let's go see if we can check that out. So, telescope is now moving. We'll see it come in. And let's hope that we're all good here. We're going to get in here. And let's... Alright. So we're going to... I'm going to confirm where we need to be. Because when we're looking at fainter objects, we don't have the ability to see them directly in the scope. But we're going to put ourselves right here. So this is the object right here. I can sort of see it now. Okay, this is a beautiful little nebula that we're going to check out. And it's a reflection nebula. We've seen Dryer's Nebula before.
Oh, yeah.
Yeah, it's really pretty.
Isn't it part of the whole big complex there going over into Monoceros?
Oh, yeah, yeah. It is. It's right near, when we get into it, if we go further to the left of it, to east, we're going to end up seeing the Christmas tree cluster and so forth, and we're going to be going to that in a little bit too. So we're going to be doing this stuff. So we're going to actually get a new image here. There's our stars. Let's get a guide star. Oh, plenty of guide stars. I think let's take one of them and let's use one of these. Maybe this one. I have to get closer to see it. There we go. Alright, let's guide on that and make sure we can stay on it. We should. Alright, we'll give that a try. Alright, so we come back here now and let's do a 25-second photo of this nebula region. Okay, and this is our low light mode. The nebula is going to be right in here. And we're going to jump out of that and go into our deep sky mode. Deep sky mode's always fun. Alright.
Images stacking.
Yep, it is. We should see the first one coming in.
Deep sky clock event.
Oh yeah, there we go. Right in the middle, just like we want it. Okay, and so I'm going to zoom on this entire curve so we'll be able to do very, very careful movement of our black level, our background level. See that? Let's go to our enhancement. Okay, we got that going. Okay, good. So we're good here. And now we're at a gain of 250, which is, you see right here. This camera goes all the way to 600 gain. And you might say, well, why not go more sensitive? Because the higher the sensitivity goes, the more noise we get. We don't want noise. Yeah, we get digital noise and we got to get rid of it. We don't want that. So this makes it much easier for us to capture good things fast. All right, so we've got 3 already taken here. And let's go back to our histogram here. And let's color correct this. There we go. Color correction looks good. And it says PhD 2 lost its lock. It's back. So we'll keep an eye on it. And that's what we want. That's IC 0446. or sorry, IC 2167, which is the star cluster nebula. And we're going to make that our target. So that'll be up here. And when we save this, it's going to go to that directory on our server at skytourlive.org, where all of you can go and grab this shot 30 seconds after we send it up. All right, so
I'll try to post a link as soon as it's up.
okay, thank you. I haven't saved it yet, so it won't be there yet.
Yeah.
Now, you'll notice that this area has an interesting number of stars over here, but then it doesn't seem to have many over here. And then they start to get more again over here. That's because this is all a nebula, all dark nebula in here that is impeding our view. Now again, we're at like a pencil view of something we normally see many degrees of. We see all of this nebula and more when we look at it through the other telescope. But our other telescope right now, all right, this one, you can see that the clouds are out there in the desert, and so we can't use this telescope tonight at the moment. So, but notice that the clouds are dark against the sky over here. That's because there's no light pollution out there. It's really quite nice. All right, so back here in our Benson scope, 220 miles from that one, we are guiding. We've got 7 exposures done here. I'm going to drop this down, our threshold, because we don't seem to have to worry when we have a good guiding. And the nice thing is there's not a lot of wind out there right now tonight, and that's good. You know, Daryl, you're aware of how Benson has all these winds at night sometimes. Well, tonight it's not that bad. So I'm very happy, and we're going to try and make the best of it.
Windy time of year down in the desert anyway.
Yeah. Exactly. All right, let's just push this. Yeah, we're not ready to push that yet. Okay. All right.
When I was down in the southwest corner of New Mexico, just before the El Paso eclipse back in the mid-90s,
Yep.
it was 10th of May, if I remember right, about then. Might have been the night of the 9th. And it was really nice down there. Almost surprisingly nice. You know, it wasn't hot yet. I came back and told my family what a great place southern New Mexico was. And my sister and her husband decided to take their RV down there the following March.
Wow.
And what they found in March was that's when the wind blows. Southern New Mexico and Arizona.
Yeah, March comes in like a lion, goes out like a lamb. That's what they say, right?
That's what they say.
Yeah.
Usually springtime is when winter shows up here in Colorado.
Mm-hmm.
This year it's strange though. We're supposed to get maybe almost 80 degrees next week,
Wow.
which is really unusual. Like 20 degrees over usual temperatures.
I hope that makes its way here. Of course, as everybody knows, I'm up in Connecticut, 2,600 miles from this telescope. Actually, 2,500 miles from this telescope. And running it from there. So it's a little bit of a... It's a little nerve-wracking, right? When you got all that equipment out there, thousands of miles away. But I'm kind of getting used to it, you know? Kind of getting used to it. I do want to say hello to folks that are here, because I haven't done that yet. Michael Hedrick was the first one here. Hi, Michael. How are you doing? Sally Forth is with us. Hi there. Hi there, Sally. And then we have Human Garka. Hey, what's going on? I'm glad you didn't miss it. Carl Becker's with us. Kevin's with us. Hey, Kevin. Julian's with us. Good morning to you in the UK. Kurt's with us. Daisy and Zoe Amethyst is there with Lane, I believe. Hey, Lane. How you doing?
Hi, Lane.
And then we have Stan from Two Rivers Observatory with us. Nice to see you. Stuffy, good to see you, man. Sam S. is with us. Richard Spencer's with us. And Richard Minnick's with us. Hey, Richard, how you doing? Good to see you again. And then we have Rascally Rabbit and James Dugan. James, where you been, man? We missed you. You know, how's it going down there? You know, C&D Boy's with us. Nice to see you.
Thank you, Toner.
Hey, Toner, what's going on? Thank you, man. That is so cool. JSCO's with us. Ron Regier. I know Ron. Ron is he's one of my friends who's up in Rimrock, Arizona. And he's watching from up there. Right around the corner from Ron's house is a front lawn that has, I think, 3 observatories in it now. And Rimrock's a fairly dark spot. So I was originally looking at that potential, and I only voted against it because there was some light infiltrating from a nearby town that I thought was too much. But we'll see, you know. So we did choose Benson over that. Rockstar's with us. How you doing, man? You know, as we're waiting for some more data to come in for this guy, I'm just saying hello to everybody. And then I'm afraid that, you know, as we move forward here, you know, I think we're going to be getting some more equipment, I'm afraid. And I think that you guys are going to end up getting some overload on astronomy tonight. Karen Belmont's, or on coming times, actually. Michael Galea's with us. Karen Belmont's with us. Sheldon Harrison, how you doing? The Goblin, one of our previous winners of equipment, is here. Yeah, nice to see you. And Toner's with us. Hey, man. American Road Warrior. He's representing MUFON, Massachusetts. That's Eric. That's my buddy Eric Hartwig. Hey, Eric. Good to see you, man. And then, oh, gosh, we have people coming in to watch stuff. I think this is so neat. You know, good to see you all. Kevin asked a question. Since you were talking about the ancients, I was wondering if you could comment on the new SARS discovery underneath the pyramids in Egypt. You aware of that?
I saw the story. I don't profess to know anything about it.
Okay. Because I haven't read that story yet, Kevin. I'm sorry.
Supposedly like an underground city under the pyramids, something of the sort.
Yeah. I think I saw something about that, actually. Wow. Yeah, I don't know, Kevin. Sorry. Let's do this just to see what's waiting there. Yeah, we got The camera temperature is minus 17.5 Celsius right now, with a target of minus 20. So that's pretty interesting. And Ron Regier says the data is not conclusive for what's underneath the pyramid. Ron would know, okay, because whenever I have a question about petroglyphs and pictographs, I go to Ron Regier, because Ron's actually quite an authority on it, and he could do a lecture off the seat of his pants on petroglyphs and pictographs and ancient views of the sky and so forth. He's fantastic. Just sorry, Ron, don't mean to inflate your head, but you know what? You deserve it, man. You got a lot of knowledge up there. Okay. All right, so we got 24 shots here, and I think if I'm gonna, again, we don't have the hyperstar on here, but if I was going to try and capture more detail in here, I would probably have made this like a minute long, and so forth. You're welcome, Ronald. He says thank you for the kind words. Yep.
Notice you have a sort of a black splash artifact there in the lower right.
Yeah,
lower left.
that's a dark frame subtraction artifact. Yes.
It looks a lot like the light artifact you used to get in that corner, but it's reversed now.
It is the same artifact, but the dark frame subtraction is taking it out. It just happens sometimes. Okay. Well, I'll just save this as it is and see if we can pull out more data later on. Okay, so that's 25 exposures. That's good. All right, so that's a little nebula with some H alpha, red emission that we saw. Not bad, not bad. And then we're gonna just go back to our low light mode here for just a minute and take ourselves to another object that's nearby. Okay, so let's do this. There we are. Okay, so now we'll come back here. First things first, though, let's go in here and stop guiding, because we don't need to guide now. And then come over here and let's check out the other object I want to check out here. We're kind of near it, right? So we might as well look at it. Is the Monoceros region here. We've got some beautiful stuff down here. But what I'll do now is I'm going to take us to Hubble's Variable Nebula, because it's kind of like right here. Okay, so we're going to go there. Right, Hubble's Variable Nebula right here, and when Daryl was talking about this nebula being close to the Christmas tree cluster, you can see why.
Well, that and all that other stuff down below it.
Oh,
Down to the Rosette.
Yeah, that's true.
Out of frame. So
Yeah.
there you go.
Yeah. Okay.
A whole string of stuff there.
Yep. So let's drop over and pick up Hubble's Variable Nebula. And there it is. Now, every time we look at Hubble's Variable Nebula, it looks different. That's because it's a nebula. And as Hubble's Variable Nebula, we know that it's got a dark cloud in here, and there's a star inside. It's not this star here. This star actually has nothing to do with this nebula. Okay? It's just an object that's kind of in the way. But this nebula is being illuminated by reflected light off of dust grains, and inside the dark nebula in here that we cannot see here is a star, and it has apparently an orbiting cloud of dust going around it, and that dust cloud orbits the star fairly regularly, and over a period of time, weeks, we can see the change in this nebula, because the reflected light that's reflecting off these dust particles here changes. As the starlight is obscured a little bit, it'll get darker and dimmer and change its pattern. So that's why it's called Hubble's Variable Nebula. And so let's see if we can get a nice photograph of this right now. Go ahead.
We've documented this in years past,
Yes, we have.
and as Mark said, I mean, we would visit Hubble's variable here and image it, and then we'd go back and image it again a couple of weeks later, and a couple of weeks later, and its appearance changed markedly. Like
Yep.
you could see a shadow moving around inside it.
Yeah, not in real time, but you could see you could see a shadow that was apparently casting a shadow on the nebula, and that's really cool looking. All right.
Ronald's here.
Hey, Ronald, good to see you. I talked to Ronald today on the phone, see how he's doing.
And Donald's here.
Hey, Ronald and Donald. Donald Kunzer, how you doing? What's shaking? Well, the telescope's not shaking, which is awesome. Okay, that's a good star, I think. So let's go back. And we've got several guide stars. We got that one, we got that one, that one, that one. So we should be good here. So I'm going to try to take some good shots here. Let's do a 20-second shot of Hubble's Variable Nebula. It's pretty bright, so especially in this telescope. So I'm going to go into our stack low light mode, deep sky mode, and we're going to check out Hubble's Variable Nebula.
Ronald and Donald. Kind of reminds me of Huey, Dewey, and Louie.
There you go. Oh, look at that. That's really
Donald
pretty.
Duck's
Cousins, nephews.
nephews, I think.
Yeah, it was nephews. Yeah.
They
Wow.
probably didn't want to talk too much about stuff like that back in the day.
Yeah. Okay. So this is interesting looking. I'm going to move this down just to give us a little more contrast. That's looking nice. Look at those details.
Yeah, you can see the dark clumps in the cloud already.
Yeah, you can. Right here. Right here.
And that all changes over the course of days to weeks.
That's right. Let's zoom way in. This is obviously way too close. We have to let a lot of data come in to get rid of the noise in here. But so we can stay a little bit out here, and we can reduce the noise by moving this down. There it is. Look at that. Now, that's cool. So we're gonna identify this as Hubble's Variable Nebula. All right. Save that just as it is, and then we will set that to be our target that we're looking at. And there we go. Yes, I've changed the name, and that's what I want. Yep. And it will be. It'll be working. So.
Looks kind of like a harp.
Oh, it does kind of, doesn't it? Nice. Okay, so we'll start the saving process in Hubble's Variable Nebula. Good. As you can see, the guiding is working great. Guiding works good when there's no wind, so we're good. Ronald, we just talked about what this white light is. This is a reflection nebula. It's actually kind of blue. Okay, there's dust grains in here, and they are reflecting starlight that's inside this dark cloud here. This star has nothing to do with Hubble's Variable Nebula. It's just a field star. And what's happening is there is a star inside this dark cloud, okay, and it has an orbiting dark dust cloud around it. And as it passes by this direction, it'll cast a shadow on this particular nebula. And so that is something that we'll notice change over a period of time, over days to weeks. And so it's called Hubble's Variable Nebula. Edwin P. Hubble discovered it, and it was named for him. It is very interesting. Toner Lowe says it looks like the old Twitter logo. That's kind of funny.
I see a harp.
Yeah. All right, let's adjust this down a little bit more. Let's do this to kind of bring out detail. Make sure we're good over here. Yeah, we are right where I want to be. Color correct this now a little better.
I bet you could open up Hubble's Variable Nebula in your app. You're in Izabela's app, and you could actually see the changes over time.
Yes, that's right.
Because I bet you've got several exposures of it in there.
Yeah, we do. Yeah, we do. Eric Ronald is saying hi to you. American Road Warrior, that's Eric. Oh, I see. You said hi first. Yeah, this looks nice. Really cool.
It does.
Yeah, we got a nice detail. I tried to take a picture of this the other night on a private session, but the wind was so high that I got all kinds of streaks, you know. And right now, tonight, when we look at this, it's like, wow, we're doing good.
Yeah.
Every single image is coming in, and let's see where our guider is. Our guider is locked right on, so we're good. We got several stars we're guiding on. Our error is, our guiding changes are actually smaller. They're not wildly fluctuating, so we're doing good. Look at the detail in here. I'm gonna enhance this detail, see if we can see better detail. Watch this. Wow, look at, we can see some dark and light patches within here for the first time. That's neat. Let's see if we can go crazy. Let's really pump that up and see. Well, that's really exaggerated, but look at all the detail in there.
Yeah.
It used to be rather uniform, and now it's actually pretty good now.
Looks pretty turbulent in there.
It does, doesn't it? Yeah. Karen Belmont says, mini Running Man. Well, I mean, a similar idea. I mean, in terms of the color, it does have a similar color. The Hubble's Variable Nebula, you know, sometimes if light is being just reflected off the dust grains, generally, then it's just going to be kind of whatever the color of the star is reflecting off the dust grains. In this case, you'll notice around the edges, there's some brownish ridges around the edges. And we also see that there is some modeling in here and changes in here that are dark and light. And this is the edge of the black dust cloud. The dust cloud is here, and even more extensive. And this is an area where the light is peeking through. And that's what we're seeing here. It's peeking through that area.
Michael H. asks how far away it is. Will it tell that in Stellarium?
Maybe. It may or may not be accurate. Let's go see. It has a distance of 2,600 light years listed, and it could be true. I'm not absolutely convinced, because Stellarium has been wrong from time to time.
Yeah.
You know, but
Close enough.
it could be.
At least I don't have to look it up.
No, you don't have to look it up. So, yeah, I just think that Hubble's Variable Nebula is just an incredible object, you know?
Mm-hmm.
Yeah. So technically, the star that's illuminating it is a star called R Monocerotis, or R-Mon. And the star is obscured by dust, and so we see the light directly reflected by the nebula's dust clouds, and that's kind of what we're seeing there. And in terms of its location, it is in Monoceros the Unicorn, and it's actually basically the given distance is 2,500 light years, officially, if you will. Let's do this just to see if there's any additional data. And there is. Look at this down here. See all that?
Yep.
There's something additional down there. Let's, and we've got 23 shots here. Let's reduce this again. Get rid of some of that noise. Kind of looks like an octopus going through the deep sea, doesn't it, with its tentacles?
Hmm.
Or a witch on a broom.
As we mentioned earlier when we saw the area in the stellarium, I mean, you can see where the cloud is fading out from the light, but it's fading into the dark of all the dark nebulosity in the area.
Yeah.
And when we saw in the stellarium, you can see all those different objects that we mentioned. They're all sort of involved in, I would assume, that same complex of clouds.
Yeah, we had Dryer's Nebula, we had the Christmas tree cluster, the cone, Rosette. They may all be related to the same molecular cloud complex. Yep. James Dugan, it was 2,600 light years, not 26,000. But that's okay. All right, let's, yeah, and 2,600 light years is just around the corner, James. Of course. I know, right? Crazy. All right, so we're going to grab this. Now, when I hit save up here, these are going to skytourlive.org on our server, where you can go and scroll down and go into the section that says take me to cool pictures. It'll take you right into our database, and boom, you'll see it. You'll see the files, and then you can go check out all of the data directly yourself. Hello, Kevin O'Neill. Nice to see you, brother. All right. While we're waiting for this, we're going to go to 30, which is right now. We'll say save. All right. That's good for now, because I think this is a good one. So we'll say save exactly as seen. Okay, we'll go into our guiding program, and we'll stop the guider, which is performing admirably. And we'll come back into our low light mode so that we can move on to the next object here. Gosh, that's just a beautiful nebula, Daryl. What can I say?
Yep.
I first saw it in 1982 when I was, believe it or not, I know I'm aging myself. In 1982, when I was working in the observatory on the Parallax program, I actually sent the telescope toward Hubble's Variable Nebula, and I liked it so much I took out a glass photographic plate, and I put it in the plate holder, put it up on there, and I guided on a photograph to keep it in there. And it was just a spectacular image that came out on a glass plate, just like you do in the 1800s. It was incredible. You know, now it's all digital, but it was the telescope doesn't have to even be monitored anymore, which is kind of cool. All right. Let's go now to Stellarium, and here we're now going to go up to the Christmas tree cluster, but we're going to go here. We're going to go up just a little bit to the Cone Nebula. Now the Cone is a cool place, so let's just check it out. It should be fairly quick to get to, not very far away. Okay, here's the Cone right here. I recognize the stars, and I'm going to actually bring us down a little bit into and get them into position a little better so we could see them. Okay, that's good. That actually looks pretty good, actually. I'll just do one click this way, see where that takes me. Yeah, that's good. Okay, so I believe the cone is right here. And so what I'll do now is go in, get our guide star, set up the guiding again, and get going. All right, so right now, oh, here we go. That looks like that'll be great, good guiding. Really bright. It's, you know, it's flat top over there, that means that we're saturating this. So I'm going to bring this exposure down to 1 second from 2 seconds and see if we can get our peak in here. Yeah, there we go. That's better. All right, so that'll be better for guiding. All right, so we come in here, and we're going to do a 35-second shot here. So I think we can. And we're going to watch this come through. The Cone Nebula should be right here. It's going to be a beautiful dark nebula. It's just a beautiful dark nebula. Ronald says this telescope is amazing. Well, to me, the most amazing part, which is kind of weird, is that it's 2,500 miles from here, and I'm using it all the way from Connecticut. I just never get over that. I understand technology. I spend a lot of time trying to make sure that technology works, but weird, huh? Look at that. Okay, so now we have the cone right here, right? And you see it's like a cone shape, and this is really pretty. You know, yeah, there it is. Really nice. Let's go back in here. Yeah, we're guiding well, it looks like. We're getting a little bit of a fluctuation in declination. That's what that red curve is. The blue curve is right ascension. Declination's up and down. Right ascension's east and west, left and right. All right. So as we go here, we'll let this stack up.
So this is kind of begging the question.
Mm-hmm.
The orientation of the cone and the bright star to its lower left, the double star or whatever, is this yet another example of a pillar? Are those two necessarily associated?
That's a good question. I imagine that's true, but I don't know that these are the two. It might be these two.
That's what I meant.
Oh, okay. It could be
Bright
these
star.
two. We have to figure out who's where and figure out the distance and so forth. Once we get the spectrograph, we'll say, well, let's find out. Let's look at this star. So we could go into a database called Simbad, find this star, get its distance, get its spectral type, and then look at the chemistry inside the star, and that'll help us determine what the temperature is of the star. Then we can actually effectively calculate some of the parameters of the star that might lead to a pillar being formed. All such boring stuff.
When we mention pillars, folks, we're talking the pillars of creation and Messier 16 Eagle Nebula is a classic example, but we see similar pillars all over the sky where we have dark nebulae associated with bright stars or clusters.
Yeah.
And that's the solar wind or the light pressure pushing back on the dark matter, blowing it away eventually, and sometimes revealing nascent stars inside the dark pillar, like maybe what those smaller stars right there are, possibly.
I mean, these guys.
Yes.
Yeah. We have only snapshots of the present day, but based on motions of the gas, we can figure out where that gas was 1 million years ago, or 100,000 years ago, and based on the examination of these stars, we could make a guess as to whether they are old or young, and be able to figure out at what point they formed versus when this formed. And so that kind of detail will allow us to figure out a chronology. What came first, the chicken or the egg? You know what I mean? And that's something that's very important to do. Ah, great. A nice satellite went right through our shot.
Well,
Yeah, that's okay. I can unstack that one. There, it's gone. I
poor
like.
guy.
Huh?
What a guy.
I like the unstacked facility, yes. Yeah. And so, unfortunately, that one that we lost is just one that we lost. All right.
Ron Regier has a question for you.
Okay, Ron Gear says, Mark, can you briefly address the red in the background? Oh, sure. Ron, what happens is that's hydrogen. It's hydrogen gas that's glowing, and it's glowing because of bright, hot, young stars in the area that give off ultraviolet radiation, and it causes the hydrogen to ionize, where its electron jumps off the atom, and that it comes back though, and when it comes back in, as it cascades down into the atom, it gives off the energy that it acquired when it left, and that energy that it acquired is given off in the form of light when it comes back in. And that light for hydrogen, especially hydrogen alpha, is red. All right. So we see lots of glowing red nebulae in the universe. Okay. And we see a lot of that because hydrogen is the most common element in the whole universe. It's a very simple one. One proton, one electron. Okay? And the electron is in a cloud around the nucleus, and sometimes that electron is pushed away because it absorbs ultraviolet energy from nearby stars, and boop, off it goes. So that's what we're seeing there.
But then it always falls back, or another electron takes its place.
Yep, that's right.
And when it does, it emits a photon of light of a characteristic frequency, wavelength,
Yep.
which is red. In the case
656
of hydrogen.
nanometers. Yep. Yeah.
And you've probably seen green in some images too. And that's kind of a teal color, characteristic blue-green color. That's a similar process, but the element involved in that case is doubly ionized oxygen.
Which means 2 electrons are kicked off the atom when that happens. Because you got to understand that out in the vast cold of space, atoms can exist. All right, so we have atoms of hydrogen, because even though this is a region that's quote unquote hot, it's only as hot as the density of the gas around you. Because if the gas doesn't have any density, there's no temperature. It's not defined that way. So things in space only absorb or radiate. They don't have temperature. That's the hardest concept I've had to get across to people is how can you not have temperature in space when you're telling me things are hot? Because if you hold your hand up to the sun, your hand heats up. But the air around your hand heats up too. All right? If you're in space and you hid the front of the palm of your hand from the sun, this side of your hand would be very, very cold. And this side would get very, very warm. Now, because you have skin with thickness, that heat would conduct through and make your palm a little bit warmer. But if you're a spacecraft, or you're a large structure, or you're an asteroid, then the side facing the sun is going to be very, very hot, several hundred degrees. The side facing away from the sun might be minus 200 degrees, minus 275. You know, might not be absolute zero, okay, but which is minus 400 and change. But it might be pretty cold, all right? It will be pretty cold. So that is why the James Webb, for instance, has that big solar diamond-shaped array on it. That solar diamond shape, okay, that's actually a sunshade, and that's all it is. It's a sunshade. It keeps the sun's light from over 1 million miles away, where this telescope is, from radiating and irradiating and heating up the very sensitive instruments on board the satellite, the James Webb Space Telescope. And so that sunshade's always facing the sun. And that kind of limits what they can look at with the James Webb throughout the year, because as it goes around the sun, because it is orbiting, that sunshade's always facing the sun. But it opens up new vistas every time, and they can tilt it a little bit, and the telescope can move around a little bit, which is kind of cool. So a lot going on there. This is really pretty. Look at that. That's more detail than we've ever seen in the cone.
Can you punch it up a little bit?
What's that mean?
Well, you know,
Zoom in?
crank it up.
Oh yeah, I can do that. Let me come over.
Seems like the brightness hasn't increased much for.
Well, remember we're only doing a 35-second exposure, but there's a lot of data here. And I can also bring the black level down, which will increase the contrast quite dramatically.
There you go.
See what I mean? I like it. I like it. It looks good. What's funny is these two stars at the top of the cone, again, the cone is this shape right here. Okay? You'll notice this is dark. That's dark nebula. That's there's molecules in there of carbon and carbon together, silicon and other materials. And then you also have within there, we have materials such as carbon monoxide ices, ammonia ices, hydrocarbons that have been created in the depths of space, carbon-based compounds that find themselves also around the grains of these dust clouds and the grains. And basically, this is making the basic primordial soup elements in the deep freeze until they're liberated by the heat of a star, and that heat of a star can drive them around and move them, form pillars, as Daryl and I were talking about earlier. And this process can lead to star formation and planetary formation, because the point is, all this stuff you see here, this is all dark nebula. And this is where life begins. Life begins in the dark. You know.
And again, all this dark nebula, I suspect, is all common all the way back up to Dreyer's Nebula we looked at earlier.
I actually think it is. Not only that, let me just make this a little more obvious here. Look at that. A lot going on here. Let me pull out just a bit. Look at that. Isn't that pretty? We've never seen the cone this good. Holy cow. Never seen. Let me see if I can.
Huh? That's what focal length does for you.
Yes, it does. And let me add a bilateral filter here for a second. See if that helps us with some of the noise. Let's do this. Okay. Let's see if I can see the difference. Yeah, I can't really see the difference. Okay, so the bilateral filter isn't really doing much right now. I'm going to move this down just a little bit because I want to kind of knock out some of the noise artificially. Because to be fair, what's really coming in is what you see in this over-processed view. This is what's really back there and coming in. Now the cone you can see very clearly, but you got all this noise. That comes from over-processing. We don't want to do that. So we would pull this back, and this is actually the better place for us. And then we have 17 frames. 4 were rejected, but that's nothing. We actually did a good job. They're actually evenly spaced. The last one was rejected, and that's okay. And let's check our guider. Still guiding beautifully. That's good. And let's move this over a little bit. Get a little more brightness in there. Okay. Alright, I'm going to save this again once we have 18 frames. There we go. So again, these dark nebulae, these are the places where life begins, potentially. Planets will form out of dark nebulae. They won't form in the middle of a bright, hot nebula like these. Okay? They form in the dark. And so that's one of our SkyTour songs that we wrote called Life Begins in the Dark. And this is because these dark nebulae are the things that are the hot button in astronomy. because when it comes to extraterrestrial life and the potential for life elsewhere, it all begins in the dark, which is kind of interesting. Yet these beautiful nebulae are illuminated by the very stars that spawn in them. And so the hydrogen gas will glow, as we talked about, Daryl mentioned, I mentioned, and these dark nebulae will simply sit there in the cold darkness of space, and they have ice on their grains. Like I said, it's the deep freezed primordial soup of a future planet, potentially. So there's 20 shots. Let's save that. So you save exactly a scene. Yeah, go ahead, Daryl.
Mr. Django is here.
Hey, Mr. Django. That's Steven from Belgium. How you doing, Steven Smet? What's happening? I'm glad I woke up in time. Okay, I'm glad you woke up in time, too. Here, let's do this so we can capture the whole thing. Okay. Now, you see me looking this way, guys. I have a large curved screen. I've mentioned this before. This side is the observatory feed. This side is the actual broadcast feed. This side is the large screen. That side is a smaller observatory, a broadcast feed. So this is where I manage all the other things you see, like the names and all the stuff you see. Okay, so I'll be looking to the left, but I'm really looking at the same thing here that you're looking at. I know, that's a mind bender, and I apologize. Yeah. So Ronald asked and you answered, is the dark dirt then? No. It's actually tiny dust grains, unlike anything you've ever seen, Ronald, because on the Earth we have things like dirt. Dirt is composed of small silica grains that have been coupled into large molecules of other material, and so they have all kinds of other elements mixed in, and these are massive molecules to make just one molecule of what we call dirt or soil. And in space, these grains are literally like 10 to the minus 8 meters in size. They're very, very tiny, micron-sized particles. And these particles, they scatter blue light and make a reflection nebula when there's dust from a bright star that's going through them, like the Pleiades. Okay, and that scattering process is because of the nature of these particles. They're very small spindles, and they're perfectly sized and receptive to blue light, which is a very short wavelength light. And so those little spindles can take in blue light and scatter it and send it back in every direction. They're well tuned for that. So that's why the colors of the universe are primarily red, blue, and teal, which is the color of the doubly ionized oxygen that we talked about.
Can I ask a favor?
Yeah.
Can you zoom in and move to the lower left just a little bit?
Right here?
Where that little dark splotch and the light splotch above it is?
This right here?
That general area, yes.
All right, let me...
Just to the lower left of the bright star.
So right here?
Yeah, I guess we can't catch that much finer. I was curious about the dark area near center now. And then just immediately to its upper right, there's a little white area.
Are you talking about this?
No, I'm talking about where you just were.
Right there.
Right there, that's the little light area.
Okay.
And then the little stringy dark area just below it.
Oh, yeah, right here.
Yes.
Yeah, let me see if I can bring out some detail in that. I'm going to do this, which is counterintuitive right now, but let me pull this back. Alright. This might make it too noisy. Yeah, we're at 27 shots, stacked images. Well, you can see this and this dark area look like they're actually coupled together.
Yes.
Yeah. And maybe I can use this here to kind of adjust it. But again, if I overprocess, this is what we have in here. There's lots and lots of detail in here. Very cool. All right.
Okay. Thank you for trying.
Yeah, it's okay.
There's another dark squiggle just to the left of the dark squiggle we were just talking about.
You mean this?
Yes.
Yeah, well, you have them up here and here. We have these clouds here too, with some hydrogen, ionized hydrogen, over the top of them, making a glow, which seems to separate this from this, but it's logically all one part of the cone. So it's got a lot of interesting detail going on in there. Very cool. And if we back out, you can see a little better. You know, not bad. That's actually pretty. Alright, well, we'll be able to do a lot more with that once we download it. That'll be fun.
Kevin says, are all those straight lines of stars normal? We've talked about this a bunch in the past. Usually they're just happenstance arrangements of stars, in the sky randomly, but sometimes they sure do look real, don't they? And sometimes I suspect we'll see them apparently following like the edges of clouds or shock waves, like in the Veil Nebula. Some certainly appear to be related.
Yeah. Yeah, sometimes when we do see like supernova remnants, we might see an arc of stars right next to an arc of gas from a supernova remnant, like in the Veil Nebula and Cygnus, which will be up, fairly soon. Actually, Cygnus is up by around 2 a.m. So summer's coming back to us. But this is again one of the mainstays of the winter sky here is this, besides the Orion Nebula, the Christmas tree complex, the Rosette Nebula complex, are all really major players in the beauty of this particular region. I'm gonna dock up this again. Here we go. And we're at 32, so I'm going to save this here.
When you see the cone there, upper right of center, you see the brighter edges around the dark shape of the cone that some of those stars to the lower left, or maybe possibly even behind the dark cloud that we see as the cone, or what's illuminating the edges of the cloud like that.
You got to remember, this is 3D, folks, so we're not seeing everything. Now, in this location, as Daryl was just alluding to, this dust is actually much denser than the area around it, and so that denser dust can obscure any potential ionized hydrogen from showing through. But it's not just on the fringes. This is a whole area of ionized hydrogen. It's just that this dark dust is obscuring it like a little finger sticking up in the way of a cloud behind it. That's kind of what's going on there. And you have to think of it, the universe as three-dimensional. And when you do, that'll all make sense. Oh, yeah.
The big red line on the lower side of the cone right now reminds me of the like the big red wall we see when we look at the horse head.
Right here.
Yeah.
Yeah.
See it almost edge on.
Yeah. Very nice. That's a very good analogy, actually. Okay, so let me get rid of the noise entirely. All right, so you can see we have a ways to go if we want to get rid of the noise entirely. That the more exposures we get, the more we can move this over and see less noise here. But we can process out all this noise, which is nice. Hey, Fred Phone, how you doing? Fred Phone Bone.
Can you go to Stellarium a moment?
Yeah, sure. Let me just save this, please. All right. Save exactly a scene. Okay. Before I do that, I just want to find out. Okay. So Fred Phonebone says, "Can you say what the depth of this?" And I knew he had a question. Can you say what the depth of this scene is, from the brightest foreground star to the dimmest background star? Actually, that's a very good question.
That's what I was going to try to figure out.
Oh, okay. So if we go to Stellarium, we can do it. I think because we can.
If it will tell you how far away the cone is,
Yeah.
and then that bright star in the Stellarium image there is the one just to the upper right of the tip. If you can identify that star and get a distance on it.
Which I can't because this let me see, this star here maybe. This star here is part of a photograph that's included in this application, so I don't think we, well, yeah, we don't get the data on that, unfortunately, because you see how that's a photograph. This one we would. Okay, so we have the information there. We have a parallax, a spectral type, all that, and a distance. That's, unfortunately, we don't get that with the photos unless there's a star that's overlaying.
Okay.
Yeah, so I don't think that's going to work.
We tried.
We did. Now that star is in here. But it's only a star. It's not actually a star that has a given position. Let's see if we come in here. Yeah, again, another star. We don't get a given position on that. Alright, well, unfortunately, no.
Michael has a question or two for you.
In reference to my last question, I wonder what...
The one above that first.
Oh, okay.
Question for Mark.
Okay. Let me go look.
Do we have any stories of supernova or other sky events affecting animal behavior?
Oh. Not that I know of. I mean, there's no records when, in 1054 AD, when the Chinese saw the Crab Nebula explode and saw a supernova, which is a star during the daytime. I don't remember seeing any records of any animal interactions back then. Do you, Daryl? Do you have any remember?
Nope. There are human ones, though.
Yeah, there are. Yeah.
The Chinese, the Anasazi of Chaco Canyon, I think, were supposed to possibly noted the 1054 AD supernova.
Mm-hmm.
And I saw something the other day where it was another culture down in Central America. They thought noted the 1006 AD supernova.
Yeah.
So, if people are animals, the answer is yes. If you don't consider people animals, the answer is no.
Yep.
And he had a follow-up question also.
Okay.
I wonder what wolves do during a lunar eclipse.
I'm not sure about whether wolves actually really howl at the full moon. I'm wondering if part of that is a cultural mythos and some of that is actual. But I don't know what they do in a lunar eclipse. They might pull out their telescopes. Wow. So anyway, okay, we're done with this guy. I'm going to just save it one more time. And then save it exactly as seen. We'll get out of here. And go back to our low light mode. And in the low light mode, you'll actually see that, there's actually no real hint. Here's that bright star, and the cone is right here, but you don't see it. So, and that in a smaller telescope, that's how it'll look. You won't see any of that. You might see a subtle hint of nebulosity in a brighter part of the nebula, but you need a moderate scope for that. So let's go now here to Stellarium again, and let's go look at the next object we might want to check out. We checked out the cone, checked out that, and the next one that's right nearby is the Christmas tree cluster, which is right at the top end and right near this other one we shot. This one is a really interesting one because there's a lot of detail in here. Here's where we are now, and here's this part of the cluster. So we're going to go into up there, and let's see if we can actually view. Let me just back out of this a little bit. Okay, we'll pull out a little bit. You can see the blue part of the nebula is already shown up here. And again, we're kind of twisted to one side. We're at a 90-degree angle, so this is not accurate. It's really the other way. This is twisted funny this way. But I want to get the Phosphor Nebula, which is right here. So we're gonna move it so that the stars to its left. I think the Phosphor is over here now. I'm not sure.
Sure would be nice if we had a rotator, huh, Mel?
Yeah, that's right. Sure would be nice if we had some grenades.
Yeah.
Yeah. Well, the rotator we have coming anyway, so we're going to be doing that. Rotator is a very important element to everything we're doing. All right, let's just try this and see how this looks. Okay, this will be 25 seconds, and let's go in and see. We're getting a little bit of wind now, as you can see. I know it's giving me a complaint because I stopped using it. All right. Not even. Oh wait, I gotta stop this. Okay, so let's do this. Okay, that's a star that could possibly be used, but I would prefer this one if I can do it. That one looks better. Let's try guiding on that one. Okay, that looks like it's bright enough to guide on. As long as we don't get any wind gusts, we'll be good. So let's give that a shot. I can see that it's doing a little bit of movement, but it's okay. So we're going to come out of the low light mode and go into our deep sky mode. Come on, folks. Join us in the deep sky mode. I'm not focused. I've heard that before, though. So right now in the other view, with the other telescope, you can see, unfortunately, that it's very cloudy up in the Sonoran Desert. And you saw the clouds just move. Okay, all right. So here we are at the Christmas tree cluster, and it looks like I probably could have moved that to a slightly better location. Once we have the rotator, it's going to be so much different. Okay. So we got those stars up there. Okay. Okay, here's the beginnings of the Phosphor Nebula over here. I'm going to stop it for a moment and bring this down more, just to make sure that we can capture what we want to capture. Trust me, you'll like it. Okay, so let's see here. Wrong way, Feldman. Okay, and then this guy. Okay. One more. Alright, I think that is good. Now let's go back in our guiding program. Stop it. Yes, I
What are
know.
you,
What's that?
what are you trying to do?
The phosphor is all up in here, which is that beautiful pillowy red hydrogen diffuse nebula coupled with that gorgeous dark nebula mixed with it. And I just would like to show people that.
I'll do that.
Okay. Okay. So I think that we've got 2 stars here. Let's start the guiding process. And so we're guiding on a star just down here, very faint. We got 2 over there, 3. So this could be enough. Let's try it. And this one will be a 30-second exposure, actually. Alright, and now out we go. Now, for the record, I'm also, if you look down here, you can see the names of the filters. We have a radiant filter, which I'll explain in a minute, and UHCS, which we've always used with the other telescope and this one. We have the gradient, and then we have a dark frame capture and just an open with nothing in there. And that's something that we want to, we don't ever just shoot open because we won't ever see as much detail. Rocket City Astro. Yeah, the guiding is, it's interesting how this is working. We have wind out there, so we're getting some error, but you notice it's stabilizing now. All right, and we do have some, you can see the guide stars we got here. And very, very odd, okay? But I'm watching them guide very well regardless. Phosphor Nebula is all in here and here, and so this when it starts to visualize, it'll look really pretty. Let's do this just for a minute, just to pull this out. Yeah, now we can actually zoom in a little. Okay, and come back here. You'll see some of the details in here become much more apparent in a bit. Yeah, a lot of detail in this nebula, which we just never saw before. Very nice. Evening wear, nice. Remember that commercial?
Yeah.
Swimwear.
Soviet fashion show.
Yeah. Swimwear, nice. Ron Regier says the greenish blue is ionized oxygen. It's possible, Ron, but in this particular nebula, let me color correct first and make sure that there's not a color correction required. That the curves seem to be lined up. So this bluish green here, this is mostly reflection nebula, which is dust that's reflecting and scattering the blue light from these bright stars. But there may be oxygen here, so it might be coupled up with that. Now, once we have the spectrograph, we can actually take a sample of this and see oxygen if it's there and be able to determine exactly what's in this nebula. So that's kind of what's fun about this. We can look at the dark nebula too that's being illuminated by light and get a spectrum of that too and figure out what it is. Some of this I'll do offline and not live, but I think it's really a neat ability to do. Just by looking at light, we can make all these determinations. That's pretty. That's cool. Ron says, interesting how the universe segregates the ionized particles. It's actually the particles themselves making atomic transitions, Ron, when they come back into the atom. The electrons in different atoms will absorb, the same energies, but when they cascade back into the atom might have more shells and have more of an internal structure that's more complex, say, than a hydrogen atom. Hydrogen atom is very simple, but it still has a bunch of shells. You have the Balmer series, the Lyman series, within a hydrogen atom for the different types of transitions that can be seen. And with oxygen, it's even more complicated because oxygen is farther in the periodic table, obviously. And so that's something that we would also look at and say, well, these transitions of these electrons can get very complicated. And so one thing to keep in mind is that even with the hydrogen atom, when that one electron cascades back into the atom, it doesn't just give off red light. Okay, it only gives off red light if it goes to a specific level, energy level in the atom when it cascades to its final resting spot. And that cascaded final resting spot is called N, as in November. N equals 2, the number 2. If it gets to that second energy state, then the color it gives off is this red light that we characteristically see in these nebula. But it can also give off blue. It can also give off other colors. Depends. It can give off hydrogen delta, hydrogen beta. And so it depends. But the hydrogen alpha is the most dominant one that we see. But it gives off other types too.
Basically, different quanta, aren't they?
Different. Did you say quantities?
Quanta.
Oh yes. Quanta is, as you might guess, is related to quantum, and that has to do with distinct energy levels in an atom. So when he's saying different quanta, he means different quantum states. An atom isn't a free-for-all. It's not like a cloud where you can be anywhere in the cloud you want. Okay? If you're orbiting in what's called an orbital in an atom, then the particle can be anywhere in that cloud, but it's in a specific cloud, a specific energy state, energy level. Okay? So those specific energy levels are the things that we are very keen to study. I had to take some water, sorry.
Yes.
Look at that, it's beautiful though. It's starting to look really pretty.
Would you excuse me a moment?
Yep.
Please? I'll be
Yeah,
right
of
back.
course. Okay, so the fox fur is developing nicely. Let's see if I can... There we go. Now you see this dust and hydrogen emission that's kind of in this cloud, and you see blue showing through here a little bit and over here. So you can see that this is all mixed together, right? We have brown dust mixed with some hydrogen emission going on, mixed with some potential oxygen, as Ron Regier suggested earlier, and with also scattered light that's reflecting off of the dust in there, making this a true reflection nebula. And I do like to color correct every now and then, just to make sure that our colors are accurately represented. Very nice. Quanta are bundles of energy, yes, effectively. And there's quantum states. And an electron can go to several different quantum states within an atom as it's cascading back in or as it's absorbing energy on the way out. And if you put a small amount, let's say, of ultraviolet energy into an atom, the electron might go to a higher quantum state, a higher quantum level in the atom. And if you give it a lot, it could come right off the atom and leave the atom. In other words, it leaves home, and it could potentially leave home forever. But then, if it's just near the atom and then if it collides with other electrons out there, it may fall into its home atom or another atom. It doesn't matter, because atoms share electrons all the time. I'm going to show you a trick when you minimize and make it smaller. You see some more detail than you're used to seeing, but now you can see the whole thing. Look at that. That's really pretty. So this is nice. Evening wear, nice. Very nice. Let me do one thing. I'm going to turn off the mask here, and that will allow us to view it with a little less noise. Look at that. You almost see the depth now in here, don't you? You can almost see depth in here. It's a very interesting location. So I look at these areas right here, and you know what I think of? I think of these are future locations of potential planet formation. In the dark nebula in here, you got to understand, like this piece of the nebula right here, that's a dark nebula. That's a dark cloud, probably of many molecules of all kinds of icy particles that are, a slurry of potential new planetary formation material. But also in there is a lot of hydrogen gas. Now, the hydrogen could be self-collapsing gravitationally and could form a star. And when you have a gravity center like that, a gravitational center, well, then you're going to get a disk around it. I could explain the physics of why disks occur in space and not just clouds. But take my word for it. We see disks forming around newly forming stars. And those disks of dust can produce clumps, and those clumps could be planetary bodies in the future. So when we look at something like this is, several light years long right here. There's a lot of dust in here, but if you flew your ship toward this, you could probably fly through it and never even know you went through dust. Like for instance, in these dark nebulae, the density in here, to go to one of the questions about the full depth that we were talking about in here, is another question. It was a great question asked in the chat. This dark dust cloud here, the number of atoms per cubic centimeter, or the size of a sugar cube, you might have only 30 atoms in here, maybe 30,000 in a fairly dense cloud in the size of a sugar cube. Now, the air that you breathe has like 10 to the 26th atoms in it, in a sugar cube size. I mean, it's massive amounts of density difference, many orders of magnitude. And so when you look at a dark dust cloud, you're just seeing a long distance object that's actually very, very tenuous. But you're seeing it from a long distance, so it looks more dense, like a cumulus cloud on the ground. Looks very, very dense to you until you fly through it in a plane. Then it's just like, well, it's all fuzzy now. Same kind of thing. Matter of perspective.
I'm back, by the way.
I know, I could tell. All right. Christmas tree cluster. We're going to save this image with annotations. And then get out of here. Set the target name too. And save it. That's beautiful. That's really looking pretty. That's going to make a pretty photo. And save it exactly as seen. So when I say save exactly as seen, this is what you get. This is up on the server right now. Well, in about 20 seconds or so, 30 seconds, this will be up there. All right. So this is what you get. You know, and it's available to take down free. All right. And if you want to join our Patreon, which you can see at the top right there above, you know, depending on your Patreon level, we'll give you a fully processed version of tonight's photos as well. And that's something that we would love to do for all of you. Hey, Daryl, thank you for putting up the server.
Yep.
All right, we're going to go to 25 images here, provided we get to 25. Okay, we lost this one. I guess let's go back and look here, see if there's a problem. Okay, no. We had some wind, but it recaptured it. That's good. Okay.
Karen Belmont has a question.
Okay, what is her question?
Do you need rotation around a gravitational object to form a moon or object of density?
Oh, very good question. Do you want to take a stab at it, or do you want me?
Go ahead.
In the universe, nothing is standing still, Karen. So when objects collapse, they start moving, and so that motion can translate into small orbits of particles going around each other. And what happens is that they tend to end up forming a disk. Now, there's some physics in there that I can explain for how an accretion disk, as it's called, is formed. But we see that a lot, and so the rotation is induced by the gravitational collapse of something, whether it's a dust cloud or hydrogen gas. And so that rotation will start forming a disk around the object. So once you have an accretion disk, then all it takes is for just a little bit of disturbance, or what we call a perturbation, to that dust cloud to form something to clump. And that clump, in the absence of anything else around it, that clump will attract more and more particles, because that's now a concentrated gravitational concentrated gravitational location. And so the stuff will get bigger and bigger and bigger. Next thing you know, you've got a planet that's going around what could be a young star in formation. So that's how that works.
It's called conservation of angular momentum.
Mm-hmm. Okay, so we're going to get out of here now.
Karen, when you look up in the sky, everything you see, from the biggest star to the smallest planet to the single little molecule, probably, everything you see is spinning.
All right. That's correct. You're right, obviously. All right. I'd like to take us down to this guy right here. All right, we'll head down to it's called the albino butterfly. And it's actually a really neat little object. And there it is, right there. Now it's kind of small, but with this particular telescope, we actually have the ability to see it quite nicely. So we're gonna center this up here. Okay, so one more little jaunt. That's good. And if I do this and get it, okay, now we have it there. That's the albino butterfly. It's labeled as the object NGC for New General Catalog number 2440. All right. So now we'll go in here, and I'm only going to do a 20-second shot of this, and I'll tell you why. It's actually fairly bright for this particular telescope, and we don't need a whole lot of exposure to capture this. So let's go into our low light mode. I'm sorry, our deep sky mode. And I probably should have actually got a guide star before I did this. I was probably so the first one's going to come in kind of weird and bad. That's my fault. Yeah, see, it's a little bit. Actually, it's not bad. All right, so let's do this. Tell it to guide. Let's see what it thinks it found. Well, it found the star center, so let's see what it does. Okay, so here we see, if we back this out. Okay, let's back this off our black level here, just to the left of the curve, as we always do. And you can start to see this beautiful red and bluish green in there. That's really cool.
Looks kind of like a bee to me,
It does, doesn't it?
like a honeybee or a bumblebee.
Yeah. Honeybee. Yep. So you can see that beautiful O3 doubly ionized oxygen in the quote-unquote wings of this albino butterfly. The albino coming from this coloration here. Looks like it has one lobe and two lobes, and then the same on this side, hence the name albino butterfly. This is probably a bipolar nebula, which is typically what we see with some planetary nebulae. They have lobes on them. They go predominantly in one direction over the other, and that's kind of what we're seeing here. This is sort of an albino butterfly, you know, the look. So when we come out here, you can see right here, you can see this wing on the left side, you see this wing on the right side, and it looks like it's kind of going on this direction, on that axis. And that's kind of what the albino, where the albino butterfly gets its name, is from that structure that we see there. Let's see if we can darken that up more.
What I see, the wing on the left looks like it's blue on top and red on the bottom, and the one on the right looks like it's red on top and blue on the bottom. And there's actually more to it than what I just said, but that sort of reminds me of when we look at the Dumbbell Nebula.
Yeah.
Around the periphery of the dumbbell, I mean, we see a lot of green, and we see particular red areas that are sort of opposed to each other.
Yep.
And how they may represent something involved in the rotation of the white dwarf, or whatever's, you know, causing the emission.
Yeah. Causing the outflow to be in the orientation that it is. There's a number of types of bipolar nebulae too. I do find this one to be fascinating. I actually found it the other night when I was looking, and realized, oh, this would be a good one to show, because we tried looking at it with the Sonoran scope, but the Sonoran telescope, the problem with the Sonoran telescope is only that it's meant for wide field views, you know, and this one is not. This one is meant for looking at close-up things. Sonoran telescope is meant for looking at wide field views. As I said, had it been clear, we would have been using this telescope tonight as well. But as you can see, we've got clouds out in the Sonoran, so we're unable to use it tonight. But that's why we have two telescopes and not just one. because otherwise you wouldn't be doing much of anything. Oh yeah, so this is cool. So we've got 12 shots taken here. Let's see what our full... Okay, so our full width half maximum filter is working pretty well there. That's good. Good, another one. Yeah, so I'm going to add... I didn't save it yet, I don't think, but I should just leave it. I'll save. And save exactly as seen. Awesome. Now let's go look at our guiding. And there's still one more thing to do here before before we really jump into using this particular guiding system in earnest. And that is that we have to do what's called a dark library for this camera. You notice how it has this sort of gray background? Ideally, we'd like it to have, a background more like this. Okay? And to do that while maintaining the stars, even faint ones, we have to create a dark library for this camera. There's several cameras on this telescope up there. Okay? There's one right there. You can see it. In fact, I might be able to just show you that if we zoom in a little bit. Okay. This right here is the guiding camera, which you see right here. See that right there? That's the guiding camera. And then this is the photographic camera on the back right here. So we have the guider and we have the photographic camera. This large object is a filter wheel. This is the thing that has all of our filters that you see over on that right side here over here. Okay, and so that is what we've got going on right there. So we're utilizing both the guider and the sensor camera that actually capture the image. Yeah, look at that go, huh? Hey, Lucky Luke, how you doing, man? Toner low. Game player. Looks like something out of Galaga. Actually, it does, doesn't it? Looks like one of the Galaga ships. Psst, 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 psst. Yep. Cool.
I was always more of a, what do they call it?
Asteroids?
No, not jogger. The jumping frogs.
Frogger.
Frogger. Thank you. That, and there was one called Joust too, which I really. It was like guys on big flying birds jousting with each other.
There was one too that was interesting, called Berserk, and it was robots, and if they saw you, they go, "Stop the intruder!" Kill the intruder, intruder alert, and you have to kind of always manipulate yourself around them. Of course, we had there was asteroids, right? Of course, famous triangular little ship with singular polygon asteroids. It was like very cool too. Space invaders, naturally. Yeah. Burp, 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 psh, psh, psh. It's kind of cool. Oh, spaceship from the Jetsons. That's right. That was a spaceship from the Jetsons. I remember that. Okay, so let's darken this up. Let's see if we can drop a little more of the noise out. Oh, look at that. That's really pretty. Really pretty. We're going to do one more thing here in just a second. I'm going to All right, we got 24 images here. We're going to stop at 25 on this guy. See if exactly a scene. Oh, time flies tonight. Okay, and then I'm going to try this. I'm going to move down here and take this and move it way down here. I want to see if we've oversaturated the core of the albino butterfly. I think we have, but to see the outskirts of it, look at that. Look at the different shapes. Aren't those incredible? Shows up a lot more now.
I think I actually see a sort of a red stripe running from the very top of the left-hand wing diagonally across the body of the butterfly and then over to
This?
the right-hand wing.
Like that?
No, diagonal.
This
From
here?
the top, well, that's the bottom, but then up at the top.
Okay, I see this.
That loop on the left side goes all the way around to the top of the insect, near the top.
I mean, this guy.
Uh,
You need way to have a cursor of your own.
yes.
You notice, though, that with more time, we now definitely see that this is O3 ionized oxygen here. You can see because it's actually very nice and blue-green. And as we move back like this, we'll be able to see that even more clearly.
Well, that shows what I was saying. If you look at the right-hand wing, the one that's farther down, on the top of it, it's quite red.
This?
Yes. And I think that red goes across the nose of the butterfly to the upper left and touches the top of the left-hand wing.
This here?
It's like an ear shape, yes.
Right there.
So,
A very complicated piece there, and you got some dark material in here. Definitely O3 here. It's that teal color that we love so much.
yeah.
We got hydrogen emission in there.
And the left-hand one has O3 in it also. It's not as bright as the one on the lower right.
Yeah. Kevin,
The
thank you for
upper part
coming,
of
by the
left
way.
hand.
Yeah, sorry there, hold on. Kevin, thanks. I'm glad you could stop in for a while. We're almost done anyway, Kevin, so you've managed to waste another several hours with us. Thank you so much. Hope you have a good evening. It's never a waste of time, of course. I'm joking. All right, so 34 changed, 34 of there, and we'll do that. Save exactly as seen. Nice, all right. So, let's see if we have room for one more. We'll find out in just a second. Let's go back here.
Give them a showcase object.
Oh, I know which one I'd like to show them, and you know what I want to show. Right near it, too. You thinking Rosette?
Yeah.
Mm-hmm. Yeah, I had M47 on the list, but we'll skip that tonight. All right, the last evening for tonight, last object for tonight, actually, will be the Rosette Nebula, which is right here. Rosette is a beautiful, gorgeous nebula, and tonight it's going to actually show beautifully. So we're going to go up to it. I'm going to turn this off. And we are going to bring in the Rosette. You'll see the cluster. There it is. That's the central cluster in the Rosette. And this actually might be a good position because it's turned kind of 90 degrees to what we're seeing in here when I get to it. All right. So when I move in, you'll see it's here. And we're actually turned in such a way as that we might be able to see a lot of detail in here. So let's, and this here too. So let's find out. We'll do a quick shot here. Let me just start our. Yes, I know you can't do it. Start photography. Guide stars. And let's do this. Try and capture more guide stars. Let me move this up to 1.5 seconds. And let's add just a little bit more in here. So now let's do this again. There we go. That's what I wanted to see. Okay. Now we have 1, 2, 3, 4, 5 guide stars. And so this should be a beautiful image. So we're going to come up here and take us to 25 seconds. I'm going to drop this down to 200 gain because it's really bright. We don't need that much. And now we'll start going. And this will give us the beginnings of our Rosette Nebula. We should see some dark material in here.
Mr. Django mentioned my wife would buy me a Rosette C11 for my retirement should I accept. I said, heck yeah, exclamation point.
Yes, what is wrong with you?
There's actually, I don't know, maybe not. It would work very much like Mars hyperstar system. I think it's F2,
Yeah,
remember correctly.
it is.
In some ways, you may find it rather limiting. I know when the Rosses came out, they're not cheap and they're really cool telescopes. There may be a steep learning curve with it, and you'll be stuck at the wider depth of field, the wider field, like with Mars hyperstar.
Yeah, which is why we got this one.
Yeah.
This is a artifact of the dark frame subtraction going on here. I would like to change that, but I don't have the ability to do that right now. Okay, so there's that red star. So if we come in here, we zoom into this. Where's the red star? Is this the red star? No. It's interesting that there's a red star in here. I'm wondering was this red star in here before? I guess we have to consult the app. I'm wondering if this red star is potentially new. That'd be kind of cool. Actually, probably not though. I have to look here and again because we're like 90 degrees shifted. Yeah. Okay. All right. Let's do this. Okay, I don't want. I think we have to move this, but I have got to bring this in more so we can pull out data, as you can see. Yeah, that's more like I was trying to do. That's the center. I want to move this down. So let's just do that right. So we're going to come back here and move the cluster down a little bit. And move it down. Let's see. Is this going to do it? Yeah. And then this will take it that way. Alright, so this will be a better view. It'll show us the dark nebula over here. And move that over again. So a relatively nondescript area, right? And let me also do this. Let me do no, I won't do any of this. Okay. Alright, so I'm not going to do the dark frame subtraction on this exposure. Let's see how that looks. Alright, this will be 25 seconds.
You had some fine details starting to show up in that last exposure.
Yeah, so I'm going to see if I can do without the dark frame. So let's go into deep sky mode. And let's see if we're still guiding okay. Oh no, we're not. Okay. That's right, we're not. See? Ta-da! Alright, let's get out of that. And let's grab some stars. Why did that not do? That should guide very well. I think this selection is much better. Okay. Let's see what this does. We have to get on the curve. There we go. We got some dark stuff in here. That's what I wanted. There we are. This is the dark material I wanted to show, so that's good. Okay, we're good. That's 2 now. That's good. Looks like we got a faint satellite in here. Okay. Let's also turn back on the unsharp mask to get our detail up, level up. There we go. Nice. Start to see some nice detail in here. Well, that's pretty.
Ronald has a question of you.
Okay. What is Ronald asking?
He says, Mark, do you have a monthly calendar for the objects of the seasons?
That would...
He asked you, so I didn't say anything.
No, you could certainly say something. Ronald, I don't, because there's so many resources available that talk about that. But that would be, I guess, I should share where that resource might be. I could do that too. I mean, the skylive.com is really good because you can just see them all at a glance.
Back in the day, Ronald, we used paper books.
That's right.
catalogs.
And planispheres.
Yeah, Burnham Celestial Handbook, stuff like that.
I have every volume.
So do I.
Yep. Okay, so we got that.
And after a while, you just
You know
you
your
know
way.
you know your way by the time of year. It's like now we're getting into galaxy season.
Yep.
Uh, probably Messier Marathon season too.
I know. Someone asked me about that the other day.
Yeah. I haven't actually looked up when the best times are this year. It
Mhm.
varies a bit year by year. Dark of the moon, stuff like that.
All right, we're getting some wind, so well, maybe the full width half maximum is less on the border. Oh, it is. Depending where you go, this can change. Yeah, I should try bringing it up and see how bad it'll be. Yeah, because these were good and that was fine. I forgot about that. So this next one should be green. That's pretty right there. I mean, I could move it over, but it's the last object, so I won't do it. There we go.
Well, you can still see the red star down at the bottom right.
Yeah.
There was a little interesting looking white wisp just to the left of it.
Yeah, that's that central, it's like a C-shaped thing that we actually captured a lot of times with this telescope so far. You know, in the wide field view, it doesn't really show up as much.
Yeah.
But in this one, it actually shows up really nice. So let's bring this all the way to the peak so we can kind of get a better hook into that dark material on that side, and then I'll bring the brightness up of that. Look at that. Look at all the convolutions in there, guys. Now, you're seeing like this glob right here. Okay. That glob, we have a blob right there. We have a blob right there. And you'll see, as this fleshes out, you'll see a number of distinct blobs in here. There's a little one right there. Little one right there. Okay, and so on and so forth. Those are objects called Bach globules. And Bach globules are well known to be, I would say, early star systems and formations potentially, and very likely early star systems. And let's just zoom in a little and move over. Okay, that's pretty good. So you can see there's some more up here. In fact, the more we look, the more you'll see. And if we go down to where we don't see any or very little noise, okay, this is the settings for having 7 frames. Okay. So we want to actually, right now we're going 7 and 7 we were captured, or 8 we captured, and 7 that were lost. And that is something that you know, is due to wind getting in the way. Even with the guider that's still guiding on that star, there is momentary back and forth, but it does recapture it. So, all right, let's see here. Now let's pull this up really far. Okay. You can see some beautiful stuff in here. There's a Bach globule right there. Now this nebula is about 5,000 light years away. So knowing that, and knowing I have a calculation in Photoshop that I put in, so that if I zoom in and measure the size of these globules, I get an immediate answer to how big they are in light years, based on the distance of the nebula. And so it'd be a fascinating thing to figure out how big these globules are and compare them to the thoughts about how big our original solar system dark cloud was, and see if we're actually possibly looking at another star system in formation out there. I would say yes. Okay, that's 10 so far with 9 rejects. I won't make you sit through 20 or 30 exposures because that's just a lot. So we got 11, so I can save that. And I'm going to do this one more time. I'll save it with annotations. Okay, good. So I hope you guys had a good time tonight, looking at these different objects tonight. That was pretty cool. We got to see some neat stuff. We saw the cone, we saw the Christmas tree nebula, Hubble's variable nebula. We saw the albino butterfly. We are looking now at the Rosette. We saw the Dryer's nebula, but it required more time. But that's all right. Toner says, this is a great stream. Thanks all. Oh, you're more than welcome. James Dugan said he had a great time. Fantastic. Thank you. Yeah, please hit that like button. Hit that like button, guys. All right. Well, I'm going to see if we can get the 15 exposures in our stack. And if we can, I'm then going to save that, and we'll end on that, because look at, we're getting some nice detail in here, which was the goal. All right, there's 15. Okay. 15 saved, 15 done. Okay, guys, thank you so much. This was wonderful. It was so good to see you all, and I hope you have a good evening, and we'll see you the next time we do this. Maybe day after tomorrow. I might do tomorrow if I can find some cool objects that I want to see special. Maybe we'll do that. All right. But hey, we'll talk about it. Anyway, you guys have a good night, and we'll see you again. So good night, everybody.
Good night, everybody.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming light for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real, like a gleam. Lift your eye, up so high, across the stars beyond the sky. Sky Tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky Tour is bringing the views, every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky Tour is bringing the view,